My name is Daniel Nenny, and I'm the founder of SemiWiki.com, the open forum for semiconductor professionals. Since going online in 2011, SemiWiki has registered more than 300,000 members. If you're not a member of the SemiWiki community, please register as my guest. I hope to see you there. Today's webinar is titled Achieving Seamless 1.6 Terabytes per Second Interoperability for High Bandwidth HPC and AI ML SoCs. Speakers today are Matthew Burns. He develops go-to-market strategies for Samtec's silicon-to-silicon solutions. Over the course of 25 years, he's been a leader in design, applications engineering, technical sales, and marketing in telecommunications, medical, and electrical components industries. He currently serves as Secretary of PICMG. Madhumita Sanyal is the Director of Technical Product Management for the high-speed Ethernet PCIe and D2D IP portfolio at Synopsys. She has over 20 years of experience in ASIC design and the application of logic libraries, embedded memories, mixed signal IPs, and design methodology for SoCs in high-performance computing, automotive, and mobile markets. This is a live webinar, so put your questions or comments in the chat box and we will respond during the Q&A. You will get a link to the replay after the webinar. Okay, let's get started. Over to you, Madhumita.
Hello, everyone. Thank you, Dan. Thanks for introducing us. So today we will cover our topic, achieving seamless 1.6 Tbps interop. So this is the agenda. I will go over, introduction, triggering new protocols like UAL for scale up, UECs for scale out, and we'll cover a little bit about the 224 gig SerDes, which is underlying all these emerging protocols. And we look at the ecosystem enablement and why is it important and what are the capabilities that the SerDes need to have in order to achieve this kind of interoperability across the ecosystem with different connectors, cables in the system level environment. And then Matt will cover the interconnect topologies, the cables and connectivities available today for 224 gig. And he will cover the interop setup demonstrations and also a little bit look ahead into the 448 gig channels. It's so amazing that we are talking about 2 to 4 gig. It's not massively adopted yet, and still we are even looking into 448 gig. So things are moving at lightning speeds. And then we'll cover the summary and the Q&A part. So as we are all aware, in this the landscape of AI and large language models are very rapidly evolving, and what is needed is essentially real-time performance and scalability. So you can see not only in the HPC world, but from healthcare to automotive to HPC, organizations are diving deeper into the realms of generative AI and accelerated computing solutions. And this kind of demand in generative AI solutions is essentially catalyzing a growing need to accommodate the ever-expanding model sizes and the complexities it brings. So LLMs essentially require immense computational power for real-time performance. The computational demands for the LLMs also translate into very high energy consumption, because you would need more memories, accelerators, and servers those are required to fit into and train and infer from these kind of models. So HPC and organizations are essentially aiming to deploy LLMs for real-time inference, and they need to kind of deal with all these new challenges which are emerging. But no single GPU or XPU or any AI accelerator can support this kind of computational demand for AI workloads. So you would need tens and thousands, and maybe in near future hundreds of thousands that of these GPUs and XPUs, AI clusters that needs to work together to share this kind of processing load. For example, Llama 3 would need 700 terabyte of memory and 16,000 accelerators for pre-training itself. And then it's kind of what we are seeing is models are having the doubling the processing parameters every 4 to 6 months. So this mass scale of parallel processing and the continuous growth have essentially put a lot of stress on the network fabrics that is bringing together the AI clusters and basically the interconnects, because there, one aspect is this compute, and the other aspect is you have to move the data from one of these accelerator to many hundreds and thousands of them. So the interconnect that needs to transport this data between all of these AI accelerators needs to kind of parallelly and continuously move alongside through the interconnects and the system. So the emerging standards like Ultra Ethernet and Ultra Accelerator Link (UAL), these are the consortiums that have emerged on top of the existing protocols like PCIe, CXL, and so on. These are formed to address the needs of these AI model sizes and parameters, and with their long list of new innovations. So both of these Ultra Ethernet as well as Ultra Accelerator Link are addressing the need for the larger AI clusters with the need to meet the higher bandwidth, lower latency interconnects, and essentially that would enable the massive AI clusters to be scaled both out as well as scaled up. So we talked about scaling out and scaling up. So in order to support this computational demand of the workloads, AI clusters actually have to, via the network fabric, it has to scale out, and within the rack of a single pod, it has to scale up, which means the AI clusters needs to work together as one massive compute. So one hand, we see Ultra Ethernet that is addressing the need for high performance and vendor agnostic links for connecting up to million nodes within this massive AI network. And on the other side, UA-Link 200 is addressing the scale up network, which is providing also similarly high speed and low latency links. It's connecting up to thousands of AI accelerators. So these are the two industry standard protocols which are making it possible to expand the processing performance and scale without the vendor lock-in. It is giving flexibility and investment protection to HPC data centers and high performance computing, system makers who are building and modernizing this kind of HPC systems. So with Ultra Ethernet, it would support up to 1 million nodes for a massive AI scale-out network, and UA-Link would scale up to 1,024 AI accelerators. So underneath this high bandwidth, low latency interconnect is the 224 gig SerDes that is running under the hood. And it's built on it has to be silicon proven, and and only 2 to 4 gig SerDes would be able to enable the bandwidth of 1.6 Tbps for UEC and 800 gig with 4 lanes, 200 gig per lane for UL Link. And of course, UA link also would deliver similarly, as I said, 200 Gbps per lane, and also the memory sharing capabilities for the scale up or the accelerator connectivity. So there's different industry standards for 224 gig SerDes that's ongoing, like IEEE and YF. They are leading the way. YF is working on 224 gig LR spec, the long reach spec, while IEEE is developing the 200 gig electrical spec, and the draft 2.0 is by May, has to be ratified. It's going to be expected to be ratified by May 2025. So these standards are very crucial for ensuring compatibility, performance across different implementations of 224 gig SerDes. Things are still evolving, and every aspect of the ecosystem, not only the SerDes, but the package, the cable, the PCV vendors, everybody has to come together and contribute and work together to make this feasible solution for UAL and UEC both. So, and as you know, with 2 to 4 gig, everything doubled. So the PCB loss to connect to the ASIC and the front panel, that is much worse at higher Nyquist than at 112 gig per lane. And this essentially requires the improvement for the PCB material with lower losses, connectors, that those are coming closer to the host ASIC, and they are adding more retimers, PCBs, even flyover cables to, with much less loss than the PCB. So with all this kind of environment improvements within the PCB package, as well as the SerDes and cable connectors, so the reach has to be determined with everything working together. So we were talking about the 2 to 4 gig SerDes. So with the different kind of implementation aspects like accelerators or switches or retimers or optical modules or network interface cards, these are all part of the scale up as well as the scale out fabric. And the interface, they're going out with both chip to chip within the rack and outside the rack is the 2 to 4 gig SerDes. So as you can see on the right hand side, there are different kind of interfaces and the interconnects that we just mentioned. So it could be like from the ASICs to the front panel. It could be through the PCB or through the flyover cables, or it could be even the co-packaged connectivity, the connector already co-packaged with the ASIC to the front panel. And then with the help of either the passive copper cable and what we are seeing today with while the ecosystem is working together, the DAC with passive copper cable might not exceed 2 meter. And then we would need the active copper cable where you have active components. It could be just the CTLE analog front end or the retimer itself within the cage of the active copper cable. And then it could be even optical interconnects if the reach needed is more than 5 meter or so on. So because the whole infrastructure of the data center racks are not drastically changing, although the interface speed has been doubled. So as we just mentioned, the interconnects need to talk to not only just the next rack or the trays or the compute trays with each other, but maybe go for 2 meter all the way to 10 meter reach. So all these different kind of channels had to be I would say put together along with the SerDes in an environment where the SerDes architecture has to be looked at in terms of the capabilities of the equalization, because it needs to equalize both shorter and long reach kind of channels. And on the right hand, so the left hand side is showing the, all the different kind of channels. So with the Nyquist at 2 to 4 gig, you can see, the channels that we see today can vary between, 13 less than 13 dB to all the way to 50 dB. And what it means for the SerDes architecture for 2 to 4 gig is, again, it has to be, it is essentially a DCDSP based architecture, but every block needed a performance upgrade because of the doubling of the Nyquist. The analog front end, the AFE bandwidth increased, then analog to digital converter have reduced noise. The overall PLL jitter got dramatically brought down because the signal UI is now reduced. The DSP needed very strong equalization capability to equalize like a 50 dB kind of reach. And MLSD is essentially very, very important and a must-have for this kind of performance. But the challenge here is to do all these, and when we are talking about the switches with the 200 plus lanes, it's not only to keep the performance intact, but as well as the power cannot be doubled. So the SerDes architecture needs to be able to accommodate both very shortly reach channel with lower power and long reach channels with very reasonable power. So how do system implementers, they can kind of forecast, because they have not, fully have their systems, overall system ready. So the initial startup point would be having a simulation environment. So the simulation environment will mimic the signal integrity and the crosstalk as impact for many, many lanes switching together. So what is shown in this particular slide is a system model where you have the transmitter IBCMI model, then you have the package extracted, and that could be, the package needs to have the crosstalk impact of hundreds of lanes, and then you can put the channel in between the interconnect that might cover from one tray to the other compute tray, or one rack to the other rack, and different kind of channel. It could be NPC, DAC, whatever, and then going to the receiver IBCMI model, the abstract model, and you have to put together this kind of system environment and simulate the channel to kind of forecast and predict the system performance, whether you see an open eye on the receiver side. And of course, that's a BR, or the bit error rate, is one of the measurement that you would look at, and the spec specifies 1e minus 4. You would need more margin there across PVT with different process voltage and temperatures. And of course, you would need to look at the FEC performance as well, and look at the kind of how these pre-FEC and post-FEC are kind of relatively comparable across the PVT. And then that essentially would give you a very good understanding on the on how your system channel would look like. And then in silicon with a 40 dB or 45 dB or more, you look at the, you can once you have your own channel, then you can, with the exact silicon with a 224 gig SerDes, you can look at that overall performance. And you need to include both the near end and far end crosstalk in the model, as well as the silicon performance when you are checking with the SerDes, as well as the interconnects and cables of your system. So in terms of, we talked about, how a system implementer would look at building their system with 2 to 4 gig SerDes. Now there's some of the examples where, as the 2 to 4 gig SerDes cannot work in silos, just the performance of the SerDes alone cannot essentially give the full, the performance of within the, it has to work with the interconnects and then the cables and the connectors, be it near package, co-package, as and over passive and optics and so on. So here are a few examples where 2 to 4 gig SerDes have been is in a loop back with transmitter going to the SciFly from Samtec HD chip cable assembly and coming back to the different MCB and going to the receiver, as well as 1 meter DAC and MCB configuration. And this is also with the chip near chip assembly with 40 dB reach and so on. So these are the few examples, and now I would hand it over to Matt to kind of go over the interconnects that are dominating the 2 to 4 gig ecosystem right now.
Yep. All right. Thanks, Dan. Thanks, Madhumita. And we appreciate our listeners joining in. So, Madhumita did a really nice job of setting the table, showing how several applications are changing system topologies within data centers. A lot of that's being driven by AI, ML, GPU clustering, disaggregated computing. We're starting to see conversations around disaggregated memory, things of the like. So as system topologies within the data center ecosystem continue to evolve, and Madhumita also mentioned this, there's a need for scalable, flexible, high performance interconnect solutions. And Samtec has tried to look at that holistically at 224 from the front panel to the back plane. So, this slide sort of encapsulates our strategy for 224 interconnect for any type of application. Starting at the front panel, and we'll talk about these all in detail. OSFP is very popular. It's become one of it's become the de facto front panel pluggable solutions for 224, whether copper or optics. The unique advantage or the unique differentiation that Samtec offers is that we offer a flyover version using our ultra low skew twin-X cable on the back end of that. So instead of having the signal, once the OSFP module, again, could be copper, could be optics, plugs into the cage, instead of having those signals go off the edge card into the edge card connector down to the PCB and then route throughout the system, it goes from the edge card to the contact of the edge card connector, and our twin-X cable is directly connected to the contact on the edge card within the OSFP assembly. That's not new. It's not a new concept. This flyover concept, direct attach on the back end of the cages, has been on the market probably since the 56G. Actually, we started working on this on the 28G node, but it really started reaching a inflection point at the 56G performance node, and just continues to manifest itself in copper at 224. When 224 started being conceptualized a handful of years ago, there was a lot of chatter, I guess you could say, within the industry that everything had to go optics, even inside the box. But we've seen, the industry has shown that copper is a reality, going from the front panel to the ASIC. So, what type of interconnect solutions does Samtec have around our ASIC? And Madhumita mentioned some of these. We have our SciFly HD family. Again, we'll go in more detail about this as we move forward. But SciFly HD really has two use cases. There's a co-packaged interconnect option, which actually sits on the same substrate as your system ASIC, so that places the interconnect as close to the system ASIC, and we don't care what the system ASIC is. It could be a network switch, it could be a GPU, it could be an FPGA, it could be a CPU, it could be a transceiver. But by placing the N2 of the flyover, close to the ASIC, you eliminate the need for BGA. So it's literally for BGA attached. So literally the signals are coming out of the pads of the ASIC, going to the substrate, and then routing over to the pads on the interconnect. So at 224, this system architecture is saving, depending upon the application, somewhere between 5 and 10 dB of signal loss for insertion loss on either end of the interconnect. So it's a very clean, it's a very high performance, it's a very it offers very clean signal integrity for these next generation 1.6 T ports that Madhumita was talking about. For those applications where something on a substrate doesn't make sense, we have our near chip solutions, our SciFly HD near chip, or ASIC adjacent solutions. Again, these are defined or are targeting using ultra low skew twin-ax to route from the system ASIC to the front panel or the backplane. We'll talk a little bit more about that going forward. We're starting to have conversations or they're starting to see industry needs also for 224 mezzanine style applications. So the SciFly HD contact system is being used within our high density mezzanine arrays, SciFly HD mezzanine arrays. And again, that allows for PCB stacking on top of each other at 224. And then we're looking at various backplane solutions, not only in the traditional backplane sense, routing traces over that, but also looking at 224 cabled backplane solutions as well. So just getting into a little bit more detail of the system, I mentioned our SciFly HD. We'll talk about the SI performance here in just a few minutes. SciFly HD is really designed as an ultra high density co-packaged cable to substrate or substrate to cable solution, depending upon the viewpoint that you're looking at it. It does offer the highest density interconnect in the industry at roughly 170 differential pairs per square inch. The illustration here on the left represents what could be described as a 100 terabit network switching architecture. With each port, you obviously can see there's 16 ports there. Each of those interconnects can handle 64 differential pair, 32 lanes, running at 200 gigabit, so 6.4 terabit per second per cable. So highly flexible, highly scalable, very easy to use. Designed for high density interconnect or packaged substrates, which we've mentioned. In addition to designing the contact, Samtec has also been developing in parallel performance of our next generation ultra low skew twin-ax cable technology, our high-speed cable technology, which supports 224, both from a clean insertion loss, return loss, and crosstalk standpoint. This is the first generation of twin-ax cabling solutions where we've got the skew down to 1.7 picoseconds per meter. Historically, before the 224 node, we were looking at 3.5. So by lowering that skew, that helps to improve the performance of the overall system. We've demonstrated SciFly HD at trade shows over the last 6 to 12 months in various form factors. The solution again is highly flexible, highly scalable, and we're happy to see market adoption of these 224 interconnects going on right now. So, one of the questions we get is what's some of the performance characteristics of these types of applications? And as I mentioned, in the previous slide, we have both the co-packaged copper and the near chip connector. So the illustration there on the left shows the advantages of using SciFly HD CPC, where the connector attaches directly to the substrate of the system ASIC. So, looking at a use case where you've got roughly 300 meters of cable, routing from the system ASIC to the OSFP port, a 1.6 terabit OSFP port on the front panel, you've got roughly a loss of 14.5 dB at 56 gigahertz. Obviously, that's Nyquist for 224 PAM4. In some applications where, instead of using a cable on substrate technology, you want to have a near chip solution, there's going to be some signals that break out from the ASIC to the substrate down through the BGA package and then route through some vias back drilled on the carrier card or on the motherboard, depending upon the application, and route to a SciFly HD. That same channel is going to have roughly 19 dB of loss. Again, assuming 300 millimeters, a certain gauge of wire, and then the impedance of the system. So, you know, this is a real use case system. 19 dB, you know, given the fact, or 14.4 dB obviously gives you longer cables on the outside of the system with longer DACs, or requires less signal integrity being done with silicon being added, whether that's redrivers or the like. So the root of this is the ability that we have to have ultra low loss on our raw high-speed twin-X cable. So, you know, this shows a very flat, clean insertion loss response of the cable itself, you know, from DC out to 60 gigahertz, given a, you know, particular Nyquist frequency. So, you know, for the 32 AWG at 56 gigahertz, you're talking roughly 14 dB of loss over a meter. And then for the 34, you know, at 56, you're talking about 18 dB, you know, around 16 to 18 dB. So, you know, when you combine the best performance, you know, the highest performance twin-X cable in the industry with very small, very densely designed contact system like SciFly HD, you get a nice combination solution for routing systems, whether it's, you know, again, AI acceleration, HPC, networking, architecture, storage, or the like. And without getting into the specifics on a customer basis, you know, we're seeing huge interest in these applications across the data center, and a lot of it's just because we can support the 200 gigabit over long distances. So, you know, a couple questions have come up on SciFly. You know, what does this system look like? Obviously, it's not just, you can't just wave solder a PCB connector on a substrate. It's more of a system solution, and that's exactly correct. This is just a mock-up of the system architectures that we've been working on with our OEMs and the OSAT so far. You have your silicon, again, ASIC, GPU, network switching IC. You know, it doesn't really matter from our perspective. You have that attached to a substrate. You have the connectors attached to a substrate. Typically, there's going to be some type of application-specific stiffener that helps to hold the connectors in place, but also keeps the you know, the force applied to the substrate when it's attached to the PCB in the package uniform, so that there's no warpage on the system. You know, general use cases in the past, OEM works with Samtec, OEM works with an ASIC vendor, and then they design their PCB and go to a PCB design house. This is a different use case model because it requires the use of OSATs to, you know, working with the OEM, the ASIC vendor, the interconnect vendor, maybe mechanical substrate, but it's not impossible because we're seeing it being done, and this type of system integration is really required to implement the 200 gigabit channels that Madhumita referenced for AI, ML, HPC data center applications that we're seeing right now. So a little bit more detail about the front panel. Our OSFP solutions we offer both in 112 and 224. They're designed for belly-to-belly compatibility, which increases system density. We offer anywhere from 1x1 to 1x6 gang ports. There's a variety of heatsink solutions available to help with cooling and with thermal relief within the system. Again, we talk about the flyover technology with our ultra low skew twin-X high-speed solutions. And then our OSFP solutions have really been designed to, you know, because they can support 200G, support N2 options both with SciFly HD or SciFly near the co-package or the near chip. One question that we get asked a lot is, how does Samtec handle the sidebands, the power, and the signaling that goes into an OSFP port? You can see that on the bottom of the connector or the bottom of the cage, we have press fit contact tails for low speed control and power positions. So, you know, other solution providers may provide a secondary cable to attach near the ASIC, but we find that just putting those pins within the cage itself simplifies system design and simplifies cable management. So what does this system look like in a real world demonstration system? So this was this is one of many interoperability demonstrations that Samtec and Synopsys have put together. So this is using Synopsys's latest 200 gigabit Ethernet IP with a physical layer chip. The signals obviously pass through our high density RF connectors, going to a MCB and an HCB that have the SiFly HD NCC cable assembly on it. There's roughly a meter of cable between the two connectors, and then the return back to the transceiver. So think about it as being transceiver, RF connector, RF cable, SiFly HD NCC cable, RF cable, RF connector. The entire channel loss is roughly 40 dB at 56 gigahertz. This is one of the channels that Madhumita referenced earlier, stressing the need to show interoperability between your IP, your silicon, and your interconnect. So over that 40 dB channel, pad to pad, we had a BER of 3e to the minus 9, which again, very clean from an SI standpoint. So Madhumita asked, and we're starting to ask, Samtec's seeing this, Synopsys is seeing this, the industry is seeing this. It's great that we've got interoperability at 224, but we got to start thinking about 448 interoperability. And I look ahead, I put question mark and exclamation points in there because I think that's kind of where we're at right now. In terms of what's next for 448, nothing is official per se, because there's a lot of standards bodies working on this, OIF, IEEE, OCP, I'm sure there's others. There's also input into where 448 is going from the semiconductor standpoint, from the copper standpoint, from an optical standpoint. But where things are as of today, and when I say today, I mean May 6, 2025, subjectively, and at least where things tend to be leaning, it looks like the semiconductor ecosystem is going to be supporting 448 PM6 encoding, which gives you a Nyquist frequency of around 86.7 gigahertz. And for optics, the optical infrastructure is going to leverage the existing PAM4 encoding, which gives you Nyquist at about 112. Why is that? We could spend hours going into all those details. Don't have the time to do that today. Optics can handle a lot higher frequencies than copper can. I think everyone that has an understanding of basic physics, electromagnetism, appreciates that. And that's one of the big influences for the differences between the PAM4 and the PAM6. How that's going to transition from sending 448 PAM6 over copper to 448 PAM4 over optics. There's a lot of details that need worked out, but we have some of the smartest engineers on the planet working on that from an SI standpoint, from a semiconductor standpoint, from an IP standpoint, test and measurement, and they're moving rapidly towards coalescing around a final recommendation. So we'll see that soon. What Samtec is seeing in terms of interest and demand for 448 interconnect or for 448 ecosystems is testing what these channels may look like. So, having a platform that can handle 448 PAM6 or 448 PAM4 with various loss profiles from a few dB all the way out to several dozen dB is a necessity. So, we've talked earlier about how Samtec has a high density bullseye test point system. This provides, it's basically SMA replacement. You get about 4 to 1 space savings using a surface mount bulkhead versus discrete compression mount connectors. That eases assembly. It simplifies use within a system while also giving you microwave test grade coaxial cable to board arrays and maintaining test grade SI channel performance. Samtec recently introduced our Bullseye ISI evaluation platforms. The advantage of these ISI platforms for testing 448 signals is the fact that typical ISI platform only has one channel. And you have to change those connections from a short trace length, say 250 millimeters, all the way to a long trace length, call it 500 millimeters. Well, we have around 13 different channel lengths on these ISI platforms, but they're supported by eight trace lengths. So you can actually do parallel SerDes characterization and validation on these ISI platforms. As far as I know, this is the only parallel ISI platform on the market. So these are highly configurable, scalable, both for physical and programmatic testing of 448. So Samtec has two versions of these kits, both a 70 gigahertz version and a 90 gigahertz version. The 90 gigahertz version is clean beyond 110. So each of these platforms can support, or the BE90A can support 448 PM6 and 448 PM4 testing as well. So far we've talked about, you know, looking at things from the IP side that Madhumita did a nice job summarizing. We've talked about the interconnect that's required for implementing these 1.6 terabit per second ports. But where can we go for more information? I'm going to turn it over to Madhumita. She'll talk about the capabilities that Synopsys has.
Thanks, Matt. Yeah, so from Synopsys, we have, you know, we talked about the 2 to 4 gig UAL, UEC, so we have the full solution across several foundries with the PHYs, the controllers, the security, the verification IP, as well as the full PHY plus controller capabilities in ASIC, in FPGA. And we are also, you know, differentiated in terms of the PPA as well as the full solution latency and you know, power optimization standpoint, area optimization standpoint, because the full data path is visible to us from the PHYs all the way to the controllers and the security modules. And we have been testing with very dense SoC integration aspects with the packages and with cable connectors like Samtec. We have performed a lot of demonstrations across last 2 and more than you know, 2.5 years with 40 dB plus channels and so on. So we have a very comprehensive solution, and it is built on our legacy of more than 20 years of Ethernet experience, and that's where we kind of see a lot of adoption of 2 to 4 gig UEC, UAL, and we are very excited to help our customers to build their full system. Thanks.
And just a brief summary of Samtec's 224 and 448 interconnect solutions. We gave a very brief introduction into our product portfolio today. Obviously, you'd need a lot more time to delve into how to implement a system design or a topology design using such interconnects. We're ready and available to have those conversations with OEMs or OSATs listening in today. Not only do we have the product portfolio, but we back that up with our technical experts, our signal integrity specialists, our field applications engineers, our application engineers, online design tools, world-class customer service to support any high-speed, high-performance application. Talked about our portfolio. We get tons of questions at Samtec about how to implement high-speed signals, whether that's 224, 448, or other applications. A lot of it is focused or around you know, SI 101. So recently we updated our SI handbook that really is targeted at whether someone's an experienced SI engineer or someone's just learning the field. It's a good way to refresh the fundamentals or to learn the fundamentals for the first time. So for more information on that and our latest and highest speed signals, you can visit our website or email us as shown on the slide here. So with that, we're going to turn it back to Dan, and he'll field any questions that the attendees may have submitted.
Great. Thank you, Matt. We do have some questions. First question is, what about 224 optics? Are there any 224 gigabytes PAM4 interconnect solutions that can support both copper and optics?
So that's a great question, Dan, and that's not the first time Samtec's received that question. Typically what we're seeing, at least from Samtec's perspective, is there are solutions in the market implementing co-package optics, but we think that there's a path forward, or we're confident that there's a path forward where using the same interconnect like SciFly HD can present options both for copper and optics within the same interconnect system. This is something that we've been championing since the 28 gigabit per second speed node. We did it 28, 56, 112. So SciFly HD, because it's a pluggable copper solution, you can plug and remove the copper cable assembly. We're working with optical engine providers that can take their solutions, put it on a substrate, and then use the SciFly HD mezzanine style connectors to fit into the same socket that the cable assemblies fit in. So if someone implements SciFly HD using the what we're calling the CPX, co-package everything, can support co-package copper, co-package optics, pluggable within the same socket on the same substrate. That provides a future-proof path for OEMs to implement 224, both in the copper and the optical domain, using the same substrate connector right next to their system ASIC. So that saves a ton of system development. That provides a flexible system level path in case an OEM decides that they want to have co-package optics right on the substrate, without having to use, with also providing flexibility to use copper on the same interconnect as well. So that's unique in the industry, at least from our perspective, and it's opening doors for us right now.
All right, there's another question for you, Matt. What's the availability of the Bullseye ISI evaluation boards? What applications will they be used in?
We are ready to accept orders for those right now. We'll be launching a website on that in the very near term. So you can just contact Samtec directly for those Bullseye ISI kits. We see those being used in the testing domain a lot, Dan. So, based on the demonstrations we've had at trade shows, SerDes vendors, test and measurement vendors, IP vendors, there's a lot of interest in having a test platform, a known validated test platform that can support 448 signals, whether that's in a benchtop or more in a manufacturing or testing environment as well.
Okay. Maybe one more for you, Matt. Can you provide more details on next-gen 448 GPS PAMX solutions?
Yes, but not in 2 minutes. The biggest thing that we're waiting for, we talked about this point, Dan, about how it looks like the semiconductor companies are going to, or the semiconductor ecosystem is going to be focusing in on 448 PAM6. That's a big step because that's been under discussion, technical analysis for some time, and the optics kind of leaning towards 448 PAM4, Nyquist at 112. So, given the fact that the industry, when I say the industry in air quotes, OIF, IEEE, OCP, other industry standards bodies, once they start to formulate their formal standards for those encoding schemes, you'll start to see, the interconnect vendors, the semiconductor vendors, the test and measurement vendors coalesce around that, and you'll start to see system design, system testing moving on. So, we're probably in inning one, to use a baseball analogy, for where 448 is going. I wouldn't expect to see commercial products in system implementations before, let's call it 27. That's just a safe estimate. But stay tuned, more's coming.
Great. This question is on signal integrity and power. So, Madhumita, what are the key careabouts for 224 gigabyte on signal integrity and power integrity? Have this been implemented in interposer package?
All right. Very good question, Dan. Because as we move to 224 gig, signal integrity is crucial. And as we see, implementers are like switches or accelerators who have many lanes of 2 to 4 gig on their package. So with organic substrate, yes, it's the same. You have to kind of look at the crosstalk, near end and far end, next and fixed on the just on the package itself when you are escaping the TX and RX differential signals. Similar to that in interposer. So we, Synopsys, with because we have so many IPs across the board, we have very good experience with the interposer technology. So with 2 to 4 gig, we, it's what we are doing is we are kind of extracting the package at the, from just the die to the package, and then all the way to the interposer ball, and taking the full channel end to end, and kind of simulating and looking at both transmitter and receiver performance. So on the power integrity side, it is very crucial, because when you have too many lanes switching, there's a lot of IR drop that's happening, and then you might not get the power that is at the bump or at the ball, and then going through the interposer to the IP bump, or where you essentially need those power. So there's a lot of IR drops, and that needs to be accounted for when you are designing the full system in interposer. And how you do is you essentially take the current profiles from the IP, and that's what Synopsys is doing right now with many instantiation. Let's say you have hundreds of lanes of SerDes, then you can essentially create a power delivery network with so many SerDes, connecting them on the package, on the, some on die, some on package, and some on board. We have guidelines for that. And then with that power delivery network, you would extract the, the parameters, and then look at how it is kind of, meeting the requirements from the power integrity perspective when you run the full analysis. So that's like overall, both on the transient side as well as power integrity side. We Synopsys is kind of helping our customers.
Great. There's a follow-up question. Are 224G and 1.6 terabyte production ready for, do they have solutions of production ready available today?
Yes, so Synopsys is definitely one of the key players here with both the 2 to 4 gig PHY and 1.6 T UEC as well as UAL. We have the PHYs, the controllers, and also the full, along with the VIP and security model, the full end-to-end solution. And this has been adopted by many customers so far. So yes, we have a production-ready solution available.
Yeah, and Dan, just to drive this point home, on the front panel, those flyover OSFP cage connectors are available from Samtec to support 1.6 terabit per second ports. The 8x200 lanes there, and from Samtec's perspective, we see Ethernet there running at 200G, but there's other protocols that can support 200G channels as well that can use that same form factor.
Right. Essentially, this can also drive, as you asked the previous question, right? The solution with the PHY and the controller can drive both copper as well as optics. So we have done a lot of demonstrations in 112 gig land. We have participated at energy efficient interface YF, and we have done a lot of with the optical modules, and then the optical cables, with either directly driving on the transmitter side. Of course, the at 2 to 4 YF has been coming up with what they call a half retimed, where transmitter is has either transmitter or receiver would be retimed, but then we have demonstrated the full linear with TX and RX as well. So that is where we can enable on both copper front as well as the optical front.
Okay. Remember, this is a live webinar. If you have a question, put it in the question box and we will address it immediately. Okay, great. Another question. Which application would need to move to 44.8G? What kind of modulation scheme or what kind of work are ongoing?
Yeah, so well, I'll just give the Samtec's take there, and I think we address that to a degree. If you look at OIF, they're looking at it from, they're defining their the electrical channels, channel 448, short range, very short range, mid range, long range, and things like that. So there's an ecosystem of support companies, the IP providers, the semiconductor providers, the interconnect providers, the laminate providers, working with OIF to define those 448 channel lengths, channel loss budgets, and the like. Again, where that looks like it's leaning towards, nothing is definitive yet, is the fact that on the optical side, you're going to see 448 PAM4, Nyquist 112. On the semiconductor side, we're likely going to see 448 PAM6, which gives you a Nyquist of 86.7 gigahertz. So, once those channels get completely defined within OIF, within IEEE, and they start getting adopted by OCP and other industry standard form factors, that's when you'll start to see implementation from the ecosystems and their various areas of expertise. Madhumita, I don't know if you have any input there as well.
Yeah, so I think the question is in terms of which application. Definitely it would be chip to chip, and I think it's accelerator to accelerator links, the scale up, where 448 gig might be adopted sooner than the other applications. And UAL has already talked about 448 gig by end of 2026, and we see customers are also, the users and implementers are also interested in HPC platform even within the rack, chip to chip, and forming the whole accelerator clusters. So that's where I think 448 gig will move faster than we can kind of imagine, because 2 to 4 gig is also not widely adopted yet, and we are talking about 448 gig now. So as Matt mentioned, that copper again, it will for backward compatibility, optics will have to stay with PAM4. Copper might go to PAM6, just that the bandwidth need, but then again it will add a lot of more complexity on the FEC, the forward error correction side. So it's always a trade-off, and that's where Synopsys is also closely monitoring. Synopsys is also working with Samtec on this, looking at these 448 gig, the full end-to-end performing simulations and looking at what, whether PAM4, which channels can be equalized with PAM4 or whatever would require PAM6. So those are kind of works that's ongoing, and we are all, Synopsys is also contributing to the IEEE as well as OIF, the workshop, the AI workshop that is right now ongoing with the 448 gig. So yes, a lot of interest, lot of work, and it's exciting.
Great. That's all the time we have for today. Thank you all for participating in the SemiWiki webinar series, and have a great day.